So this is going to be hopefully quite informal, quite interactive. I've made some slides to sort of help guide through the tutorial, which are in the folder where the talk slides are, and they have some links that will be useful. So STRAUSS, as I mentioned before, is a Python package. And so going on to the second slide, we've got some links. I think the easiest way to get you guys to have a go at this is through something called Google Colab, which is where you can run like a Python notebook in like a virtual environment, and you don't have to worry about getting STRAUSS installed on your computer. So to like avoid the troubleshooting issues there. But I will say, if you do want to have a go at like installing this locally, like after this, then there's instructions on the STRAUSS GitHub, which is also linked on the slide, the bottom link on the slide, which is here. So this is what the STRAUSS GitHub page looked like. I just switched my tabs. And there's instructions on how to install that locally there. We'll go back to the slide. So if you follow this first link, it's to a Google Colab version. And what you will need to do is click on File and save a copy in Drive. And it should say that right at the top of the notebook. There's also an HTML version. I appreciate and apologize, notebooks are not super accessible, but there's an HTML version of the notebook which you should be able to follow along, and it has the sounds embedded so you can play them. Or if you just don't want to touch the code, you can just read the static version on the HTML. There's a link to this which will take you to a GitHub page which looks like this, and it'll say, we can't show you this because it's a big file. And there's a little download button on the right-hand side of the screen. And once you download it, you should hopefully be able to open it, and you'll get an HTML, an HTML file of the notebook. So it should look a bit like the notebook. It'll say important first step at the top, which isn't relevant if you're looking at the HTML file, but it's just a copy of the notebook. So I'll let you get set up with that. I saw there was something in the chat. Is someone monitoring the Zoom? Oh, thank you. Amazing. That's great. So yeah, there's the links at the bottom. It's just which might be useful for the future. The STRAUSS GitHub, which I showed you, which tells you how to install locally, and the documentation. There's detailed documentation, which I sort of refer to in this tutorial. So, sorry, I need to pick a tab and stick with it. So did everyone manage to open the Google Colab that wants to? There's no enforced thing. Great. So a bit more about STRAUSS. As I mentioned, James Trayford is leading the development on this. I'm working on it a bit for my PhD and using it. James was sad not to be here. He's getting married. So I'll try and do it justice. It's super flexible. There are lots and lots of options, and I appreciate there's a lot of stuff in this tutorial and it may seem overwhelming, but we are also working on making it a more user-friendly version, and we're specifically building an app for science communicators to be able to make sonic content for their like planetariums and stuff using STRAUSS, which has a friendly user interface. But we're going under the hood because I what some of the people here might be interested, and you know, there are you need lots of choices. That it depends on the goal of your sonification, what you're trying to communicate. So Strauss aims to give you those choices. Yes, it's all open source. So I appreciate, we appreciate any feedback, and sometimes it's not always the most intuitive way. It's just, you know, choices were made at the beginning of the programming journey, and so today, if you have any feedback and any questions at any point, just ask and let me know. So at the bottom of this slide, I've put sort of the workflow of a Strauss sonification. So to go from data to audio, we have these different classes in the code. And so we start with the score, which defines like how long we want the sonification to be. And you choose any notes that you might be using. Might not always feel relevant to choose notes if you're using like atonal sounds, but we choose our notes in the score. And then we have a class called sources, which is where we define our mappings and how the data is like mapped to the sound properties. And at the moment, there are two special types of sources in Strauss. There's one called events, which is like the example I showed, where each data point is played as a discrete sound. So with the different transient events with the supernovae. And then there's a source called object, which is where we treat the data like it's an object that's evolving continuously in time, and the sound is continuously changing. Then we choose how we're going to generate the audio with our generator class. And we've got a built-in synthesizer. We've got a sampler, which can use audio files or sound font files. And then there's this special case, which I also mentioned in my talk, called the spectralizer, which is where you treat your data like a spectrum of sound frequencies, and you produce a sound directly from the spectrum. Then finally, there's, well, another class we use is the channels class, which allows you to map the audio to different speaker setups. So for this tutorial, we stick with like mono and stereo because that's sort of the technology that I assume you have access to. But there are ways you can create your own speaker layouts, like in theory, any custom speaker layout, but we've used this for like planetarium shows where you've got 5.1 surround sound. Yeah, and then all the information from these classes are brought together with the sonification class, and then you get your audio at the end. So I tried to explain this in the notebook that I've made. I apologize because there is a lot of text, but I thought it would be useful. You can, like, you've saved a copy in your drive, or you've got the HTML copy, so you can refer back to this if you want to try and use it in the future, even if, yeah, I appreciate it's quite overwhelming at the moment. So this slide shows you the layout of the tutorial. I think when we'll get started, maybe I'll just leave this up. It was meant to try and help you not get lost, but it's a lot of words at the moment. So we start with installing Strauss, which, as I say, we do in Google Colab, which is like keeping this kind of virtual environment in the cloud, so you don't need to worry about dependencies. And then we're using some example light curve data for this, which in the examples we use, it might not necessarily be relevant, but just to keep it simple, we're using 3 different light curves throughout the tutorial. So this is just time series data, one-dimensional time series data, flux over time. And then we're going to have a go at sonifying these as events, so where each data point is played sequentially, like discrete sound, and then sonifying it as an object, where it's a continuous sound. And then we're going to have a go at sonifying the periodograms, which are like the Fourier transforms of the light curves, which tell you what frequencies are present in in the light curves. And we're going to have a go at spectralizing those. So there's lots of different examples that you will get to create with this notebook, and different parameters you have a go at playing around with. So I left, just for reference in these slides, I won't play them now, some examples of like what events are. So these, when it's discrete sounds, an object example, and an example of the spectralization technique. And I've also, in case it's useful when you're going through, I've put visualizations, this is on slide 6, of the 3 light curves that I've used in the tutorial. So in the top left, we've got beta Persei, which has like 4 deep eclipses. So it's like a binary eclipsing system, and then it's got 4 shallower eclipses. All of these light curves are observed over a period of around 12 days. It's the same time scale for each of them. And then we've got in the top right, EX Draconis, which is, it's something called a dwarf nova. So it's a white dwarf eclipsing binary pair. So you've got regular eclipses in this light curve, but also big outbursts. So you've got a big overarching outburst pattern. And then in the bottom middle, I've got RR Lyrae, which is a regular pulsating variable. So, sorry, that's a lot of talking. With that, I will go on to the actual Jupyter Notebook tutorial, Google Colab, and I think I will start talking through the first example. And if at any point, like, I appreciate there'll be different levels of experience with Python and things. If anyone wants to go on ahead, like, feel free. Yeah. Also, some of the sounds, if you have headphones, you might want to listen on headphones. There are some bits where we experiment with spatialization and stereo. But yeah, so does anyone have any questions before I start going through that? Are we okay? Cool. But yeah, please interrupt me if you have any questions. So as I said at the top, if you haven't already, please save a copy in the drive, because then you'll be able to run it yourself. And so if you're not familiar with notebooks in Colab, there's these markdown cells which have text and links in. And then also when you get to the code cells, you can use Shift and Enter together to run the cells. So to begin with, we have to set up the notebook. So if you haven't already, so we're going to section 0, installing STRAUSS. And this will take a couple of minutes to run, but you need to run the pip quiet install STRAUSS. And it says AITTS. So this is installing a variant of STRAUSS which has a text-to-speech module in it. We're still working to optimize the text-to-speech, but there is an example further down where I'll show you how that's used.
Sorry, what do we shift enter?
Shift enter. So you click on this cell.
The whole stuff.
Yes, and do shift enter, and that should run it. And then you should get these like, it'll start printing out progress bars in the output. And then, yes, of course. Yes, you can do that right now on your computer if you're in the Google Colab environment. And so what you want to run the cell underneath it as well, which you can keep going. It'll just do it when it's finished. So you can keep going through in order. So this git clone cell is just I made a GitHub repository, which is where the HTML file is, and that's got the data that we're going to use. And then,
Is there a reason
yes.
why you wouldn't just bundle all this and we click once and it would do it all? Because there seems to be 3 separate multiple steps.
Yeah, so you probably like, I think I just split it up to explain what each cell was doing. It could all be in one cell, yes. So yeah, this is all just set up. And this is a thing with Python, you always have to import modules and classes, which can be a bit of a pain, but it's just a thing that you do at the beginning. But once you have like a list of the things that you need, you sort of just copy and paste them between your code as you're using it. So once those might take like a minute or two to run for the first time. And you might get a strange like warning under the imports, but that's okay. So then from section 1, we want the data. And it can be helpful to visualize the data as well. We're going to visualize the data. We're getting data from the transiting exoplanet survey satellite, TESS, which are these light curves that I showed you in the slides, and you can keep looking at the slides. And so we've got some code under reading in data here, which will just grab those files from the GitHub repository that we've cloned. So again, we just need to run these. Shouldn't take long. And then in the cell that starts with defining a plotting function, that's just making a nice, easy function that will read these specific data. So this is kind of for this tutorial. So I can just say like plot light curve and it'll do that. And then in the cell below that, after let's visualize our data, you should be able to run that, and you will now have 3 plots. So in onto the actual sonifying, if we're all okay. So as I mentioned before, we've got these building blocks of a Strauss sonification. And again, this text is just here for your reference. We need to set up the sources, the score, the generator, the channels, and the sonification module at the end brings them all together. With this Colab notebook, there is some like extra information which I've collapsed. So when you see an arrow on its side, if you want, you can expand it and it will show even more writing. Sorry. And that's already automatically printed out in the HTML. So again, this is just like for future reference, but I appreciate it's a lot of information. So we start by defining the score. So we need to choose the notes that we play in the sonification. So it may be that we're just selecting the note that it starts from, or we want to quantify this into like bin it into notes on a scale. And then we also need to select the duration of the sonification. So then under the scoring code, you will see we need to specify the notes. So anyone unfamiliar, these lines that start with a hash, they're comments in the code. So that's just a bit more context. and they should show up as green. So here we're choosing A2 as a base note for the sonification. And at the moment, you can either define the note as in hertz, or like frequency, or you can use this scientific pitch notation, which is like a letter and a number. So it's like A to G, and I think 0 to 10 or something. So we choose our note. So we're going to do free pitch mapping. So we just need to pick a note that it starts at to begin with. And we're going to choose the length of the sonification. So this is 15 seconds. You can change these. That's up to you. And then we set up our score by calling the score class and calling the notes that we've selected and the length. So then we need to think about our data and the sources class. So this is how we define our parameter mapping choices and how we want the data to be represented. So as I said before, we can use either events or objects. So for this first example, we're going to use events. So that's every data point is being played as a discrete note. Setting up our sources, we need to make a dictionary which defines which parameter is being mapped to which data, like which column of your data you want to map to which parameter. And then we also have two different sets of limits. So we have mapping limits of the input parameters, which are, these are the limits of the data that we want to use. So you define it in percentiles, and it's like clipping the data almost. So normally you want to go from 0 to 100%, but say you want to clip out all of the bottom 5% of the data. For some reason, you could go from 5 to 100 or 5 to 95. So that's what the mapping limits are. And then we also have parameter limits, which are the actual ranges of the parameters. So each parameter has a default range when you use it for mapping. So for example, when we're doing pitch mapping, there's a default range of 2 octaves above your starting note. So that is equivalent to 2 doubling in frequencies. So we can alter these limits. If you think that changing by 2 octaves is going to be too much, you can change that by adding in parameter limits. There's a handy parameter reference page, yes, redirect me, on the documentation, which tells you all of the different parameters you can use. And then it tells you the different default ranges. So you can decide if you want to change those. And there's more details here in these collapsed cells. So let's get to our code to set this up. So the first couple of lines are defining our time and flux from the data that we have. We've just chosen to sonify our library here. We want it to be a NumPy array when we read it into STRAUSS. Then we need to set up our mapping dictionary. So we put as the keys the parameters that we want to use. So here, this is something that's slightly confusing. We always have to set a base pitch. So we're going to use pitch mapping for this. So as the flux increases, the pitch is going to get higher, but that parameter is the pitch shift. And so we always have to set a base pitch. And here we have to make it an array, which is the same length as our light curve data. So I've just set this up by saying I want an array of ones that is the same length as the time array. So it's just going to be 1, 1, 1, 1, 1. So it doesn't matter what the values are. We just want it to be constant and the same length. And then we're going to map the time in the sonification to the time on the light curve. So as time goes on, time progresses through the data. And then we're going to map pitch shift to the flux column. Then we're going to set up our mapping limits. So also slightly confusing here, we want the time to be slightly longer than the data. So the time in the sonification, because if we map it for events, if we go from 0 to 100, the very last note will be triggered at the end of the sonification. So we need to leave a little bit of buffer time to let that play. And then for the pitch shift, we want to use the whole amount of the data. So for this first example, I'm not going to change the parameter limits, but if you wanted to, this line which says p-lims, that's where we define our parameter limits. That's changing the pitch shift range in semitones. So it's going 0 to 12, so that's equivalent to 1 octave, so it's making it a smaller range. So you can uncomment this line, and then uncomment the last line in the cell, and that will implement that. So we've selected our limits and our mappings. What we need to do then is we point to the parameters that we want to use. So we point to our maps dictionary, the keys that we've set up using sources, and we're choosing the events class. And then we point to the data. So it's grabbing from the dictionary, from this mapping dictionary, and then we apply the mapping functions by setting up the limits, the mapping limits as limbs. So I'm going to run that cell. So normally I would do all of this in one cell. I'm just breaking it into bits to explain all the different things that are going on. So then we need our generator. We need to choose how we're generating the sonification. So we can use, as I said, a built-in synthesizer, or we can sample audio files. And because we're playing this data as events, so with discrete sounds for each data point, we can choose the length of note and edit that played for each data point. So these are, I think there's like 8,000 values in these data files. So we want the notes to be really short, basically. And we edit that using ADSR parameters. So ADSR is like the volume envelope of a note, and the attack is A, decay, sustain, and release. And you define attack, decay, and release in seconds. I should probably draw a picture for this. Oh, do I need to? Oh, okay, yes, yes, sorry. Okay. It's chalk. Okay. So will they be able to see here? So surprisingly well, great, amazing. I can't draw straight lines though. So this bit is the release. This bit is the sustain. This bit is decay, and this first bit is attack, going from 0 to peak to sustain level, which we define as a fraction of the amplitude, and then release is from the sustain level to back to 0. So these are more parameters we can adjust. So to call our generator into the code, we define the generator as the synthesizer, which is what we're using for this first example. There are also preset generators. So we change the sound of the synthesizer by changing the oscillators that we're using to generate the sound. There are different built-in presets, and they have sawtooth waves, sine waves, triangle waves, noise generators. So, oh, sorry, did someone have a question?
I had a quick question. I was just wondering, is this, sorry, oops. Is this the volume that's changing over the duration of the note? Sorry, I probably just missed you saying that, or the pitch itself, or?
Yes,
any
sorry, I think
parameter?
it's like the amplitude, yeah, the volume.
Okay, the volume.
But someone in here probably knows more about this than me. Yes, I
Cool.
think it's the volume. So it's like, if you have this is like the peak, and then the time overall is like how long the note effectively plays for.
Okay, so it'll be like loudest upon first moment of hitting the data point, and then
Yeah.
it's like flat for a bit, and then it'll die out.
Yeah,
Okay.
so it gets loud, goes down to a sustained level, and then dies out.
Cool. Okay, thank you.
That's okay. Sorry. As I say, someone here can probably tell you more about it better. So we load a pitch mapper preset, which uses a single triangle wave, because we don't want it to be too harmonically rich, to be able to hear different pitches in this instance, but you can also create your own presets. And so we're setting values of the attack, decay, sustain, and release. So we want really short notes. So here we're defining it in seconds, attack as like 0.02 seconds, and we don't want any sustain. So I'm going to run this cell, and the way we change these parameters is by modifying the preset. And then we want to choose our system that we're mapping this to, with the channels. And so we're going to define a system as mono to begin with. But as I say, you can choose any system you want. You can build your own custom. So we're going to run that. And then finally, we've got the sonification class, which brings together, we need to call all of the information that we've just defined. And in this example, we're also going to downsample the data, because as I said, there's lots of points, and it's really fast and hard to like hear them all. But you can experiment with changing the downsample factor, which I've here defined as n, or also changing the length of the sonification, making it longer so there's more space for the notes to play. Yeah, so we have to call all of the classes that we've just defined, so the score, sources, generator, and system, using this sonification class. I've set a downsample factor, which we then use in the render sonification command, so function. So we want to render this, and then I've put this plotting function that we predefined to plot the data that we're sonifying. And then this at the end, it's a handy function to display it in the notebook with a playback function. But if you're using a script, you can use the here function instead. And we'll run that, and you should hopefully have, you get two plots. You get on top this light curve, which has been downsampled, which we plotted, and then you get a visualization of the waveform, which is too big for my screen currently. So there's one channel because it's mono, and it's not really changing because we're using pitch mapping, and then you have a little playback. So I will play this now, and hopefully you should all have the same sound. Great. So, and if you wanted, you could go back and try changing the downsample factor. I tried to put little pencil emojis in the code where you can change things, and yeah, have a go. I will say if you want to change anything further up, like when we were, like if you wanted to add parameter limits, so I can demonstrate that actually. So I'm going to uncomment this line, which was p-limbs, and uncomment the line where we call the p-limbs. Then I would have to rerun this cell and all of the cells below to get to the generation of the sound again. So let's see, this should have changed it so there's less of a pitch map range. So it should only map over 1 octave now. So you can hear it's now lower.
Thanks. So just to clarify, this is mapping. The reason it is like lower is because that's based on the initial pitch that we had set. Or
No, so I didn't change the initial pitch there.
no, but like it's
Okay,
staying at that lower start point.
Yes.
Because that's the initial pitch that we had set.
Yes.
And then it's just going lower because we had changed the pitch
Yes,
range of
exactly.
what it's mapping to. So
Yeah.
like 1 octave instead of 2.
Yes.
Okay.
But I could go change the initial pitch and make the whole thing higher or even lower if we wanted. So yeah, you could have a go at doing that. I mean, I can demonstrate what that would do. So let's go for like C4. It's only 1 octave. As in the range I've chosen is only 1 octave. Sorry, I won't play very much of it. But just to demonstrate how it would change. So that's now a higher starting point. Okay.
Sorry, this is a sheer curiosity question and not a useful one, but what happens if you try to set it outside like audible human hearing range? Like, does it just...
I've never actually tried that.
Oh, okay.
You
Yeah,
can have a go.
Okay. See if I can break Python on my computer.
Yeah. That could be interesting.
Is it MIDI?
No, I don't think so. It's just
Yeah. It's gonna alias anyway, so you're not gonna be able to create ultrasound.
okay.
Basically, notes on the couch.
So the next part of the tutorial, so now I've like gone through that block by block. We're going to be making sonifications in like single cells. So there's an option where you want, if you want, you can choose which stars you want to listen to. So I think by default there's two stars here, Beta Persei and Extra Conus, but you can change those. So the cell under choose your stars, that prints out the different names that we've got. So if you want to change that, feel free, just list it in this star list. So now the next example we were going to try was using sample audio files. So at the moment, it requires the files to be WAV format. Again, this is something that we're working on. So this time, we're also going to use the audio caption. And this cell, I will say, if you want to run it now, it takes a couple of minutes because the first time you use the audio caption module, it has to download the text-to-speech module. But so this time, instead of using pitch shift and varying pitch freely, we're just going to change the pitch parameter, and we're going to map it to the notes of a scale. So here I've written in notes of a pentatonic scale, but you could choose any notes. And so this is like quantizing the pitch, which is a choice you could make. You don't have to. I'm not suggesting that any of these are the best way to do anything. It's just demonstrating some of the functionality. And so basically what it will do is split, like bin the data into as many notes as you have selected, and it'll put the highest bin in the highest note and the lowest bin in the lowest note. And then what we're doing, we're setting up the length of the sonification again. And again, we call our score with notes and length. And then we're grabbing our data. This time it's in a loop because we've chosen as many stars as you wanted to choose out of the 3 options. So, and this time instead of pitch shift, because we're just going to change the base pitch of each note effectively, we're mapping the flux to pitch and the time. Again, we're making the time a bit of a buffer because we're still using this event sonification. And we call, we select our sources as events and call from the mapping dictionary that we've made, apply the mapping functions. And here is where it changes. We've selected the sampler generator, and we have to point to a directory of sample files, which we've grabbed from the GitHub. So if you're using sample files, it's a little bit clunky at the moment. You have to call each file underscore note name, basically. So, and you have to have the notes that you've chosen to use. So they'll be in this file, they'll be like mallets underscore c2.wav. But that's just a little quirk at the moment. And this time for the sampler, we can load a preset instead of having to select our ADSR values. We've got like a preset template that chooses short notes called staccato. So we're doing that, and hopefully it will have rendered soon. So to use our caption, we create a caption variable, and you can write what you want it to say. And then it will automatically add that to the beginning of the sonification before it plays. So it doesn't matter how long you've said the sonification will be, that will still be the same length. It will add this caption beforehand. It does take a little while to render the first time. So I've got my first one, so I can play that for you. So here we've got Beta Persei. Again, I've used a down sample factor, and it's these mallet samples. There you might see there's a couple of gaps now in the waveform visualization, which is because there's actually gaps in the data from when Tess turns around and points to Earth to send data back. So I'll play
In
that.
the following audio, percussion mouth sounds are used to represent data points in a stellar light curve. As the star gets brighter, the pitch of note gets higher.
Cool. So again, not necessarily the best way to sonify something, but demonstrating how you can use sample files. And you should have 2 examples for that. Another cool thing you can do, rather than using WAV files, you can use sound font files, which are freely available online on sometimes dodgy looking websites. But so that's quite cool because they have all the notes and you don't need to worry about having them like named in individual files. And you can choose different instruments. So this cell here is just to grab the sound font files. From a place where they're hosted on Google Drive. So I think we've got like different types of guitars and then one sound font that is just flutes. And we can set these both up as samplers. So we'll call it a flute sampler. And this code is just a point to where this file exists in our notebook. And then guitar sampler. And so the guitar sampler has lots of different preset options. And if you don't select a preset option, then Strauss will just choose the first one. But as you can see, there's so many different types of guitar. So there's a numbered list here in the output. So from 1 to 69, there's a lot of different types of guitar. So you can choose which one you want to use, and I would encourage you to pick one from the list by changing this SF preset value. And then you set up your guitar sampler with your sound font preset value. So you run that cell, and if you want to change it, render your sonification and then change it again, you'll need to come back and run that cell and then run it again. So this time I've again chosen notes to quantize this for. I've chosen a chromatic scale, kind of arbitrary, just showing that that's something you can do. And then we've got the same setup again with the score. I've made it a bit longer this time. We need our mapping dictionary, we need our limits, we need our sources, and then this time I've gone back to editing the ADSR values, and at some point here, generator equals guitar sampler. Above that, there's a line which says generator equals flute sampler. So if you want to try making it with a flute, you can swap out those lines as you like. So I'm going to run that. And what preset did I choose? Number 32, which is jazz guitar GU clean. Interesting. And then I'll listen to the second example now. I'm not going to play all of it because it's 30 seconds, but you have access to this and you can do that if you want and change the different generator. So now I'll probably move on to the next section, which is sonifying data as objects, but like if you guys also just want to have a go through it yourself, that's fine. Sorry, I've been talking for a while. Okay.
Really cool also.
Thank you.
But I don't know if you can do this in Jupyter, but as the music or the sound is playing, is there a way to have like a vertical line that scans across the plot to see like where we are, or is that like?
Yes, that there will be a nice way to do that, and I can't remember. I'm sorry.
It's okay.
But yes, we've made videos like that before as well, but sorry.
Yeah.
Rose, the text to speech is awesome. I wish I could have time to put that in Astronify. Do you have the option for the text to speech to also do things like read off x-axis, labels, ticks, or is it just like the string you put in basically?
Currently it is just the string that we put in, but that would be something
You have plans to
really
look into
neat.
that?
Yeah,
That'd be awesome.
we're like working on that.
Cool.
Yes, because that would be really useful.
Sorry, is that?
No.
Is that a Python built-in library or what are you using?
Yeah, it's a Python library that we're using, I think.
Okay, cool.
Can't remember. Cool. So now we're going to look at sonifying data as objects. So this is, like I said, where instead of getting these discrete notes, we're going to play the sound continuously. And we're going to look at sonifying using different parameter mapping choices. So when we're sonifying data as an object, it's going to be, as I said, evolving in time. So instead of using our time parameter, it's a slight syntax thing. We're now using our time_evo parameter. So again, all this information is written down here if you want to look back at it for reference. I appreciate it's a lot to begin with. So this time we're going to have a go using a low pass filter. So this is like a technique that I described before, where we map the cutoff frequency of the low pass filter to the flux of the data. So when the flux is highest, the cutoff frequency is like the highest frequency in the sound that you're using. So you get all of the frequencies. So like if you were using a chord, for example, you would hear all of the notes, whereas when the flux is low, the cutoff frequency is lower. So you would only hear the low frequency sounds in the sound that you're using, if that makes sense. So hopefully, well, we can demonstrate this. So this time, we're going to use, instead of just one note as like a bass note, we're now going to use these 4 notes, but we're not mapping to the pitch. We're going to play them like in parallel. So it's kind of like sonifying 4 data sources at the same time. So this means when we set up our mapping dictionary, we need to create a list the same length as the number of notes that we want to use, because it's like 4 strands being sonified simultaneously. So we're making this chord, which is so the sound will have it'll be harmonically rich so that this filter will actually have an effect when we apply it. So we can set up just the pitch, because again, we need to set this bass pitch as an array with 4 elements. And then the time evolution, we want to, we can just use the time each like 4 times. And again, the cutoff parameter we're now is what we're mapping the flux to. So we're just going to use 100% of the data for these different parameters now. But I am going to put in some parameter limits for the cutoff. So we do this as numbers from 0 to 1. So this represents the fraction of the audible frequencies that can be heard at the minimum and maximum range of the filter. So when it's at 1, if the maximum is 1, then you can hear all audible frequencies. And if it's at 0, you can't hear any audible frequencies. So sometimes we want to change that because we do want to hear what's at 0, like at the bottom end of our data. So we'll change that to 0.15 and 0.95. We have a preset which you can change to make a sonification with white noise. So you can load this generator called Windy if you want to, but first we'll try it with our chord. I'll run this. So let's listen to Beta Persei with the filter cutoff and a chord. So maybe you could hear how the sound got duller when the transits happened, because you're only hearing the lower frequencies in the chord. It might be more obvious with this EX Draconis. Cool. So another thing we can do, sorry, yeah, when I built this, I was just like, okay, what else can we do? What else can we do? Including spatialization. So at the moment, as I say, I've limited this to mono and stereo. So you can, but you can use surround sound as well. So in this next example, I've just introduced some stereo panning. So the sound goes from left to right, and I don't know how this will come out of the speakers or what, but basically to do this, we've got the same chord setup. So you'll notice lots of this is sort of, you can just use again and again when you want to sonify your data. But this time, it's a slightly confusing, we have to include an azimuth and a polar parameter. So polar angle is like angle vertical to, it's gonna be hard to explain in words, like from the horizon going upwards vertically. And then azimuth is going from east to west, like on that plane. So the polar, unfortunately, you need to set both a polar and an azimuth angle if you want to include this spatialization. So we want the polar one to be constant. So we're going to set it with level to the listener. And these values are defined in cycles for the azimuth and half cycles for polar. So polar goes from 0 at the bottom to 1 at the top. So we want it to be 0.5, which is in the middle. And azimuth, basically left of us is 0.25, and to the right is 0.75. And 0.5 is in front of us, and 0 is behind us, which is a bit confusing. But that's how it's currently defined in Strauss. So we make a scaled array going from 0.25 to 0.75 that goes with the time. And this time, because we're using stereo, we need to, when we call our system, we need to say that it's stereo. I also forgot to say, we have to use this filter cutoff method, we have to modify the preset and turn on the filter. Again, this is all written in this notebook. So we'll run that cell, and now the visualization of the waveform, you'll see, has 2 channels. And again, it's a bit big for my screen. So we've got the top panel shows the right-hand channel, which is in orange, and the bottom panel shows the left-hand channel, which is in blue. So you can see how the sound is starting in your left ear and moving to your right ear. And I don't know if this is going to work, but if you have headphones, I recommend listening with headphones because it's quite cool. So I will also just demonstrate what happens when you do use the windy generator. So this just overrides the the notes that you've selected. So unfortunately, you do still have to select bass notes, but you could just pick one. And when you use the windy generator, you turn down the sound a bit because it can be quite harsh. You can hear how that's like a white noise sound with a filter, which can be useful. Cool. So the next part of the notebook is for when we've got multivariate data, or you want to sonify, that there's different ways of doing this. So again, this isn't really necessarily physical with the data that I'm using, but I've given an example of where you might want to listen to 2 different light curves at the same time, and you could listen to one through your left ear and one through your right ear. But then also you could treat them so they're like 3 different variables, and you could map each one to a different parameter of the sound. So to begin with, there's just some cells to like set up the data in a nice way. So we're getting all of the times and all of the fluxes from the data that we've grabbed already. And we're going to put these all on the same time scale. So we're just going to grab one of the time arrays, and then these are grabbing the fluxes for each of the different stars. So we've got flux underscore BP, flux underscore RL, flux underscore EG. And because we're going to listen to these 2 together, we're going to listen to 2 together, 1 in each ear. I've actually normalized them so they're all on the same scale, but you wouldn't necessarily have to do this. So it's like treating them as 2 different sources. So we're defining our sources in Strauss. And this cell here, you can choose which one you want to listen to in your left ear and which one you want to listen to in your right ear. So you can have a go at changing that. And this time we're going to pick 2 notes, and we're going to start like, so one of the light curves is going to have a bass note of F3, and one of the light curves is going to have a bass note of G2. So it's arbitrary, you can change these. And then, so because we've got 2 notes and we're sonifying 2 sources in parallel, we need, in our maps dictionary, we need the values to be lists that are the same length. So we need 2 values for each entry. So we're using our Sony time array, which was just the time that we got from one of the light curves. And then we're putting in our left and our right flux, which we defined in the cell above. We're putting 1 in the left ear, so 0.25, and 1 in the right ear, 0.75, and we want them both to be constant polar angle. We're going to use the cutoff filter cutoff technique again. And we can have a go at doing this. And then again, this will definitely be better with headphones, but you can see even in the waveform, so the left channel is RR Lyra, and I've plotted both of these over the top. So this is in a dashed orange line, and that's coming out of the right ear, and you can see how the shape is changing. It's kind of similar to how the data goes. And then in the left ear, you're hearing the extraconus, which had this big swell, but also lots of eclipses. So again, in stereo, good.
Thanks. This is really cool. So with this one,
Yes.
how could I do all three at the same time? I don't need to do them in separate channels, but how would I put sort of all three of those together?
Yeah.
Is it just
You would
changing?
add, you would need to add another note. It could be the same, but like another note, because each bass pitch is like a source. And then you would add like 3 elements to these, and you would make each of these 3. Sorry. So we've got F3 as being given to the left one right here, and G2 is being given to the right one. So we'd need a third note, and a third, you'd add another, you could have center or whatever, you'd add another flux array there. You would times this by 3, because you'd need a time evolution for each of the 3 sources.
It's this
Yeah.
cutoff element that's really doing the
Okay.
lifting in terms of taking the series, or
The cutoff element is what we're mapping the flux to. So that's where we actually put the flux data, yes. But each of these elements needs to be they each need to be a list with the same number of elements as sources that you want to.
and if I don't set them, do I have to set them, or if I don't set them, does it map to all?
It won't happen if you don't
Okay.
set them.
All right, perfect, thanks.
That's okay.
Why does it have to be nested lists?
That is a good question that I can't answer, sorry.
Okay, cool.
It will be some weird Python thing, but I'm sorry. Yeah. So then another way to do it would be like, so there we've used the same cutoff parameter for varying the sound, but we could use different parameters, and here we're going to use all three light curves, but instead of sonifying them as separate sources, we're now treating them like different variables of the same data. So say you had like a galaxy simulation and you wanted to listen to the star formation rate, but also the metallicity of the galaxy and also something else. But rather than just comparing 2 different galaxies. So this time I've set it up so we're going to use the azimuth, which again will only work if you've got headphones or stereo speakers on your laptop, and the pitch shift and the cutoff frequency. So here in this cell you can choose which light curve you want to control which parameter. And this time we're treating it like it's one source with 3 different variables. So we're only going to set up one note, and we set up our time evolution. We set up our pitch shift. So here we've chosen it as the extraconus flux. The azimuth, again, we want it to be values between 0.25 and 0.75 because that's our left to right in front of us. So we've scaled the flux that we've chosen for that to be values between 0.25 and 0.75. And then we choose our cutoff and we set up our mapping limits and our parameter limits. Again, changing the limits of the pitch shift and the cutoff frequency. Let's see, so this one's a bit crazy because it's got 3 things going on at once. So when you listen to it with stereo, you might be able to hear that it's switching between ears, and this goes with the regular pulsations of RR lyrae. And then the pitch shift is going with the big swell with regular eclipses of extraconus, and the cutoff is going with the transits of Beta Persei. This is a crazy figure. It's not actually useful to anyone, but you can hear the sound drop out with those transits. So we'll listen to this. It's a bit crazy. And yeah, if you want to have a play around with this, then you can change which light curves you're mapping to which parameter. You can change the parameters if you want to look in the parameter reference guide. This is not exhaustive and it's already like a lot of stuff, so you know. Cool. Does anyone have any questions before I move on? Great. So the last part of this tutorial, we're going to sonify spectral data using the technique I spoke about before, where you can hear the whole spectrum at once. So what we are going to do is grab the periodograms of the stars, so it's basically like the Fourier transform of, I went straight in, yeah, sorry, I forgot how I'd set this up, of the light curve data. So it tells you like what frequencies are present in the light curves. And so in the output of this cell, you're going to get 3 periodograms, one for each of the light curves that we've been using. And you'll see these each have peaks at different frequencies. So it's like a power spectrum of the frequencies in the light curve. And so they've got distinctive shapes. And to sonify that, we're going to take the, so these periodograms have arrays of frequency and power. So we're actually going to kind of ignore the frequency array and just take the power array. And what we can do is we choose the values of frequency that we're going to map this over. So that can be arbitrary, or you could link it to the original frequency array, but you can kind of choose, like, work out what a comfortable range of frequencies to map it over is, or or scale it with your frequency array. But obviously we want it to be audible frequencies that are comfortable to listen to, potentially. So again, we need to set up a base pitch, even though this gets overridden. So this is a feature that we're looking to change, but you need to set up a base pitch as a note in our score section. And then you can set up your length of sonification. And now in our mapping dictionary, we have a spectrum parameter. And we're just going to use our power array from our periodograms. Again, putting it in as a numpy array, numpy. And we just need to assign the pitch, basically. We're going to use 100% of the data. And so here we're choosing events when we set up the sources. It doesn't matter. We just have to choose a type of source, because this spectralizer is this special case which will kind of override it anyway. But so we select the spectralizer generator. And then the important bit here is modifying the preset to change. You choose the minimum frequency that we're going to get mapped over to the maximum frequency. So you choose the frequency range. And basically, like, so yeah, the lowest frequency in the spectrum will be mapped to 100 Hertz here, and the highest frequency in the spectrum will be mapped to 1800 Hertz. We're choosing the mono system, And then this code is just plotting the periodograms. And we render our sonification, and you can hear the differences between these different periodograms. So extraconus has 2 peaks at more high frequencies relatively, and some power in the low frequencies as well. So we'll listen. So you might have been able to hear that's the 2 high frequencies, and also there is some low note underneath. Beta Persei has quite a funky periodogram with lots of, did I skip one? No. It's got more power in the lower frequencies, and they sort of they get less and less as the frequency goes up. I think this one sounds quite dramatic. Then RR Lyrae has a prominent feature sort of around the middle of the range, and then some more high frequencies as well, but less in the lower end of the spectrum.
Hey Rose, this is Amy online.
Yes, hi.
The sound sounds just like a steady sound. It doesn't.
Yes.
It's supposed to?
Yeah, so we're not playing this as time series anymore.
Right.
We're playing we're treating it as a spectrum of sound frequencies and playing the whole spectrum like simultaneously.
I
so
see.
like the power at different frequencies is like mapped
all
to
this at the same time.
Yes.
So it's not a XY
Yes.
plot with X frequency, for example. Like a normal
no,
power
so we're not
spectrum.
playing it.
Yeah.
Sorry.
Well, yeah, like
Yeah,
a normal spectrum, right, would be power on the y-axis versus frequency on the x-axis, right?
Yes.
And but you're not playing it from left to right. You're playing.
Yes, that's correct. So
Okay,
the
and
visualization.
and so what parameter indicates the power at a given frequency? Is it the volume? Then like if you have more power at lower frequencies, the lower sounds are louder?
Yes. Yeah, that's
okay.
Yeah, that's it.
All right. Sorry if I missed the
No,
before.
not at all.
Okay.
Apologies for not making it clear, but yeah, so the visualization I've got is a typical power spectrum with power on the y-axis and frequency on the x-axis, but we're not sonifying it like an auditory graph, like going from left to right. We're sonifying the whole spectrum and hearing the whole thing at once, which again isn't necessarily the right way to do this. It's just a technique, but you could certainly sonify it using the techniques that I've showed before with the events and the objects. So yeah, you hear louder volume effectively where there's more power at that frequency. So yeah.
It's like you laid a piano keyboard
Mm-hmm.
here, and you had 88 fingers, and you pressed them all on the key simultaneously, but some of them got more pressure than others. Right? So the left hand gets louder because, in this case, and then a few of them get more loudness from that key.
That's exactly it. So Bruce just gave a nice analogy of if you had a whole keyboard and you had 88 fingers and you pressed all of the keys at once, but some of them have more pressure. So some of the notes are going to be louder. Effectively, sorry, that was a short and less good version.
Okay.
But
no, I get it. Yeah.
Okay.
Thank you. I understand now.
Sorry.
If you have a source that slowly varies in time, you still want to play a Fourier transform of the window, but you want to make that window long.
So
It's kind of like breaking your time data into this way.
yeah, I guess you could like
Because you might have a variable spectrum.
yes. So asking about can you sonify like time variable spectrum or time window spectrum?
Yeah. Time
Yes.
window.
Time window Fourier transform.
Sort of halfway between what she was asking and what you.
So like at the moment we don't have the like functionality to evolve the spectral sound, but like you could manually code it, yes. So like take a spectralize like a window and then just keep adding them on, yes.
In principle, easy enough.
Yes.
Specify a time series of certain.
Yes.
Or you have a window and then wait once you get that spectrum. So then we just move it along.
Yes.
A couple more parameters.
Yeah.
It's often just very useful to get sources, but have a spectrum for them, but the spectrum does evolve.
Mm-hmm. Cool. So the very last bit of this notebook was oh, Solei's got a question.
Lizer, sorry. Can you vary like what type of sound mapping? Like, instrument is the wrong term, but like, can you vary like what type of tone sound, like the timbre that you're using for this? Like, could you use windy, like as white noise instead, or like a square wave or something like that?
Yeah. So at the moment, the default is for the spectralizer is a sine wave. But you can change the type of oscillator.
Okay.
Yes.
Cool.
And there's information about that in the documentation. Cool. I don't go into the full details, sorry, but
awesome. Thank you.
Yeah. So yeah, it's sine waves with randomized phases at the moment. Yeah, the very last part of the tutorial is kind of just for fun. You can add this orbiting effect by adding an array for the azimuth, so getting it to vary between 0.25 and 0.75, however many times you want it to. So you can change this parameter. So I've chosen 2 orbits, and then I've also added a volume envelope. So to give the effect when you're only listening in stereo that it's orbiting around you. So it's like the volume is quieter when it would be behind you and loudest when it's at the front. It's just a fun thing you can do. And we've got an example of when it's actually more useful, of a sequence that we made of planets orbiting around you. But here I've just used the spectralizer sound, and it probably won't, I don't think these speakers are doing stereo, but if you wanted to listen to it in your headphones, does it? Oh, great. Amazing. Well, I'll play one of the examples of it orbiting around you twice. And again, you can see nicely in the waveform visualization how that's changing between the ears. And that's the end of this notebook, but I would just like to say this is all open source. There's more in-depth examples on the GitHub and on the documentation page. There's do check out, there's loads of links in this tutorial, and you can check out the HTML version as well if you don't want the code. I mean, the code's still printed there, but if you don't want to, sorry, I'm waffling now. Yeah, any feedback would be appreciated. Also, I have some Audio Universe pencils that I got made for an outreach thing, and I still have lots, so I brought some if anyone wants a pencil. And that's, yeah, all I've got to say for now. If anyone has any more questions, go ahead.
You were speaking of planetariums at the end. So if I had a 5.1 speaker system, let's say, where I have a base speaker and a front speaker and 4, can I program the location of those? So that and can you actually set it so that if you use these altazimuth angle functions, it would more or less roughly put it in the right place?
Yes, you can do that. And we've done that. Like, we've made a planetarium show for 5.1 surround sound. Yeah, there's information on the documentation if you want to read about it.
Just from curiosity, since I don't know what kinds of speaker systems they use in planetariums, in principle, you could, of course, arrange them in all kinds of patterns.
Yeah.
In planetaria, do that, or is it standard 5.1 arrangement?
Most of them have 5.1, but they do have this, like some of them have fancy, I think they call it like 3D audio, where it can be anywhere.
But you could probably program that.
Yes. Yeah. Yeah. You in theory can have any array of speakers.
Outside of what you were just showing,
yeah,
but earlier in the morning you had a thing.
Yes.
And then you're scanning. Where in the documentation would I look for that?
Okay, so that is on a development branch, and you're super interested in that, right? So I can set you up with that if you want. That would be great. We can exchange details.
Okay. Yay, thanks.
There's a hand from Amy.
Hi, thanks. That was a super clear presentation. It's something
Oh,
I've
I'm glad.
that I've never experienced and can't see what you're doing on the screen. That was really well done. My question is, do you know if anyone has used this package for in other disciplines besides astronomy?
So at the moment it's mostly astronomy, but we are trying to encourage other fields, and I'm actually part of an interdisciplinary project at the moment, which is working with researchers in different fields to help them sonify data, not necessarily for research, but for art and communication as well. So we're hoping that some things will come out of that. I don't know of any specific current examples, but yeah.
So I think it was you that played a sonification about global temperature increase.
Yes.
We made that using.
Yes, we made that using STRAUSS, but that was like our team, so I feel like it doesn't count. But yes, we did that.
Oh, I see what you're saying. Yeah. Okay.
Yes.
Right.
Yes. But there are lots of, I would say, on the YouTube channel Audio Universe, which I think there's a link on my other slides. There are lots of examples, including non-astronomy examples that we've made ourselves.
Okay, that's good.
Yes.
I should have asked the question that way.
Jump in with an extra answer to your question, Rose.
Please go ahead.
Lucy Wally's a material scientist on that same project you were just talking about, and she's started using STRAUSS for her material science work, and she's looking at the she studies crystalline lattices. And she studies the vibrations at the quantum level of these materials, and these vibrations are called phonons. It's nothing audio related. That's just what they're called. And she started exploring using STRAUSS for doing the sonifications of that work as well. So I know at least one material scientist who started using.
Yes, you're right. Sorry, I forgot about Lucy. I've been talking for too long.
That's fine. And I think Dan is also thinking about using it for his work with space weather data.
Yes. Yeah, we're hoping to expand it to, there's going to be some outreach in high school kids, getting them to do projects with space weather data potentially. I think that's what Dan was thinking about. Anyway.
Yeah.
Okay, cool. So
Well,
we
I don't want
are-
to keep, I don't want to keep talking too much, but it seems like an apt time to mention the GeoSonnet project. And Bruce knows all about it, he can fill you all in who are in person. Geoscience is a sonification, a network, what is it called? A network for sonification in the geosciences. This is an effort based, is centered but not exclusively in the US to try to encourage geoscientists of all flavors, you know, ocean, atmosphere, earth, to take up sonification as a tool for communication and research. So we consider ourselves sort of an interdisciplinary group also. And that it's being sort of administered through the Sonification World Chat, which Bruce can also fill you all in on there in person. So that might be, both are available if you search for them online. If GeoSonnet has its own website. So you might be interested to check that out. Yeah.
Thank you, Amy.